talks this morning, we should all file out through the doors there and have our photograph taken. Also, tomorrow morning, Bill Martin unfortunately has cancelled his talk at 9 o'clock, but instead, Mikhail Bethera from Tübingen has kindly agreed to speak. He was giving the last talk on Friday, and his talk will be tomorrow at 9 o'clock. We've arranged a mystery speaker for Friday. So, I'd like to introduce Dan Gusfield from Isaac Newton Institute from UC Davis. He's going to talk on integer programming.
Thank you. All right, so this is mostly an empirical work. Everybody here knows about some of the difficulties in doing phylogeny, have missing entries, homoplasy. And the work that I do is actually more motivated by population genetics, but they have evolutionary trees there and mathematically very similar, except that they also generate difficulties in conflating data, but I won't talk about that in this talk, but the work relates to that as well. So most of these problems are NP hard, although some very nice special cases exist where elegant results exist. And the usual reaction to a problem being NP hard is to either move over to heuristics or anyway, in one way or another, give up on the exact solution. And what I wanted to do here, whoops, and I didn't want to do that. What I wanted to do here in this work is to see what we could do about exact computation with integer programming, because integer programming in many different problems has proven effective in solving problems exactly, at least up to some sizes. And the question really is empirical. Can we solve these problems in practice on useful ranges of data? I mean, we're not going to get to genomic size data in the population genetics arena or tree of life scale in phylogenetics. But there are certainly applications that are much smaller than that. And we've recently looked at and developed integer programming formulations. This is the only semi-theoretical issue, is to develop these integer programming formulations for about 15 problems. And then we investigate them empirically for speed and efficiency. And in some problems, the biological utility, although not in the ones I'll talk about today. I'm going to talk about, well, in the slides here, 5 problems. Probably won't get to them all. Well, here's the starting model, which everybody's very familiar with. This is the compatibility or perfect phylogeny model, where there's some ancestral sequence in this case, and we're assuming only one mutation per site in the whole history of the sequences, and down at the leaves you have the extant sequences that you can observe today. So this tree has derived these sequences, and everybody here knows, or almost everybody here I assume knows, the necessary and sufficient conditions for when this is possible, that the set of sequences must not have any pair of sites or pair of columns that contains all 4 of these binary pairs, or in the population genetics world, these are called gametes. So this is the 4 gamete test or the compatibility test. You look at your data, and if there's a pair of columns that has all 4 combinations, you cannot build a tree with one mutation per site. That's the essential combinatorial constraint. And if there is no pair of columns that has all 4, then you can. Okay. And everybody also knows, or most everybody here knows, that the set of splits of a tree uniquely determines the tree, and that's very important in what happens in these formulations, or at least some of them. Okay, so just a little bit of terminology here. Again, everybody's familiar with. A pair of sites that has all 4 binary pairs is called incompatible, otherwise it's called compatible. And one can look at binary data and determine rather quickly whether there's a pair that's incompatible or not. All right, so suppose we have we have data but has some missing entries. And we're interested in the compatibility question or perfect phylogeny question with the missing entries. First, I'm going to talk about binary sequences. So you're given binary sequences with some question marks. Those are the missing entries. And the problem is to change each question mark either to 0 or 1, now to minimize the number of resulting number of incompatible pairs. Okay? So a special case of that is simply, can you set the question marks to 0 and 1 so that there are no resulting incompatibilities? And this is what I said was a very elegant special case. In general, that's NP hard, but if somebody tells you what the root of the required tree is ahead of time, if that's part of the problem input, then there's an elegant polynomial time solution to that problem. Okay. So again, this problem, which I'm calling M1, is missing entries. You have to impute their values. And the objective function is to minimize the number of pairs of columns that become incompatible after that imputation. And there is, I'm going to describe in some detail how to solve that by integer linear programming, because it really is the basis for all the other problems. This ability to, in integer programming, optimize incompatibilities or reduce incompatibilities or detect in integer programming whether there are incompatibilities. I mean, I should say just very, very briefly, in case there's somebody who doesn't know, what I mean by integer programming is that you set up a system of linear inequalities or equalities where each variable is required to take on an integer value. And in particular, in everything that I'm doing, it's required to take on a binary value. It's a 0 or 1. And then you have an objective function, which is to minimize or maximize some linear equation. Anyway, and you have an integer programming solver. There are many out there. I'm going to be talking about Cplex. My computations are done with Cplex, which is the Cadillac integer programming solver, version 9 or version 10 in different experiments. At any rate, so let me tell you how you solve this problem of imputing values to minimize the number of resulting incompatibilities. So here's a variable yip if row I and column P does have a question mark as a missing value. And of course, that's going to be set either to 0 or 1. And then for every pair of sites or columns that might be made incompatible, I mean, if you look at the data that's given, some pairs are already incompatible. Some, they have all 4 combinations, all 4 gametes. Some pairs you can figure out could never be incompatible no matter how you set the values. And then there are some that might be, depending on how you set the missing values. So that's DPQ. That's the set of missing, that's the set of missing or deficient gametes in pair PQ that would be needed in order to make site PQ incompatible. I'll have an example in a minute. And then for each one of those pairs, AB, it's a binary pair that's in this deficiency set, we're going to create a binary variable B, which is indexed by the 2 sites and by the 2 gametes. And we're going to create inequalities that will set that to 1 if somehow the missing values have been set in a way that the sites P and Q become incompatible. Okay? No, sorry, B, not B yet. B is just if the missing values are set so that you get gamete AB in some row for sites PQ. Okay, let me give an example. So here we have PQ, and we already have a 0, 0. We have a 1, 0, but what we don't have is a 1, 1, 0, 1 in order for P and Q to become deficient, to become incompatible. So this is the deficiency set. And so the B variables, to set those, we'll need inequalities for each AB in this deficiency set. One for each row where AB could be created. And here's, for example, when AB is 1, 1, we have the inequality Y2P is less than or equal to BPQ1, 1. What does that say? From row 2, you see that we could make 1, 1 if we set from row 2, oh yeah, that is P. If we set P equal to 1, then we will have created the 1, 1 gamete in site PQ. And this is just simply says, if you set this to 1, this will be forced to 1 as well. Okay? So that happens. And then for row 4, it's a little bit more involved because row 4 we have 2 question marks, but this says if I set this to 1 and I set this to 1, then this will be forced to 1 by this inequality. Coming up with the right inequalities in integer programming is always just a little puzzle, and it's not worth talking too much about them, but usually can figure out what they are. For the 0, 1 case, that's also missing here. You have the opportunity of creating 0, 1 in row 2, row 4, and row 6. And here are the inequalities which would set the b variable to 1 if, in fact, in any one of these rows, the y variables are set so that you get this 0, 1. Okay. So we get those inequalities. That's put in the integer program. And let me just explain the architecture of this. In comes the data, and I have a Perl program which produces these inequalities, hundreds of thousands of them in some cases, and then those are fed to Cplex to try to solve them. All right, we also have a variable CPQ, which then says, have the y variables been set so that P and Q actually become incompatible? And this will be set to 1 if every gamete in this deficiency set is created somewhere in PQ. And so this says, well, I needed a 1, 1 that wasn't there. I needed a 0, 1 that wasn't there. And if, in fact, the B is set so that there's a 1, 1 somewhere, if the B is set so there's 0, 1 somewhere, CPQ will be forced to 1 also by this inequality. Okay, again, it's all just a puzzle. So CPQ is set to 1 if the y variables are set in the correct way. Now, this whole system of inequalities is actually quite small. We only have a quadratic number of b variables. M is the number of columns. Also a quadratic number of c variables, and this many inequalities. So this is a polynomial size integer program, fairly compact. So space doesn't become a great issue. And what's the objective function? Well, we were trying to minimize the total number of pairs that were incompatible, and that's CPQ. This is set to 1 if P and Q become incompatible, so obviously we want to minimize that. All right, so this has all been implemented and tested out extensively, and I'll just say for this problem, this is about the binary, and I really want to talk about more than binary. These solve in fractions of seconds, up to this range at least, for 100 columns, 100 rows, which is not genomic size, it's not tree of life size, but it's big enough to be practical for many problems. And percentage of missing values up to around 30%. That's been tested extensively. And we generate the data under recombination, homoplasy, and various things. These solve in fractions of seconds. Okay, so I'm not really big in really exhaustive empirical investigations because it depends on so many things that are questionable. But this is enough to say, yeah, this works. This is practical and could be embedded in some other things. This was Cplex 9. Cplex 10 is much faster and available now. We did this experimentation under Cplex 9. And this was just, the binary case was just published about 6 weeks ago in the Proceedings of Cocoon. Okay. Interestingly, these solutions impute the missing data correctly. That is based on simulations where you knew what it was with very high frequency. Okay. So many extensions, that's the core, and many things can be built on that. For example, the problem of remove the minimum number, if you have complete data, remove the minimum number of sites so that no incompatibilities remain. This is a common approach that's at least advised in phylogenetics. You can find that in a number of places. Of course, site removal, when you have missing data, impute values in the missing entries to minimize the solution to the site removal problem. And these two problems can be easily built on top of the first solution to M1. Let me just explain how the site removal is done. We'll have a variable di set to 1 if and only if site I is going to be removed. And then you simply add these inequalities for each site pair PQ that might become incompatible. Just add the inequality that says if they did become incompatible, this was the variable from before, if the y variables are set in such a way that these become incompatible, well, you have to remove either P or Q. And that's what this inequality says. If this is 1, in order to make this greater than or equal to 0, at least one of these has got to be 1. And then the objective function is changed to minimize the sum of these d variables, so minimize the number that are removed. Okay, now I want to talk a little bit about the non-binary case. So the history of this is I gave the talk about 6 weeks ago at Cocoon on the binary case, and then somebody asked, well, what about non-binary case, and I realized how to do that. So I've been doing the last 6 weeks or so. So what do I mean by non-binary? First of all, what is a perfect phylogeny for non-binary characters? You again have n sequences m and m sites characters. Each site can take on now one of k values, not just 2 values anymore. And what's a perfect phylogeny? Well, again, it's a tree. Each node is labeled with an m-length k-array sequence now, not just binary. And it has n leaves, one for each of the input sequences. But the crucial requirement is this. Whenever you look at a character and you look at a state of that character, the nodes in the tree that have been labeled with that state for character C form a connected subtree. And it follows that the subtrees are node disjoint. Okay, this is a very well-studied problem. Here's an example. Here we have 3 states per character. Okay, the 0 went away. I don't know. Now it's encoded 1, 2, and 3 instead of 0 and 1. And here is a perfect phylogeny for that data. All right. To see the tree, the subtree for state 2 of character B, well, all of the nodes that are labeled with 2 for character B are here and connected by this red subtree. Okay, so that's what a perfect phylogeny is. And we have 3 problems that are similar to the ones that for a binary case. If you're given a ternary matrix now, 1, 2, and 3, I want to remove the fewest sites, characters of M, so that the resulting matrix is a 3-state perfect phylogeny. So it's analogous to the binary case, but it's more involved. The TR, that T stands for 3, R for removal. Another problem, given a ternary matrix with some question marks, some missing entries, you want to set the missing entries to 1, 2, or 3 to minimize the solution for TR1. For that problem. And then the existence problem is a special case. Just is there some way to set the missing value so that there is a 3-state perfect phylogeny? Okay, so we're generalizing from the 2 to the 3. How do we solve this? Well, when there's complete data, Dress and Steele had a particular solution that is easy to use for integer programming purposes for the 3-state perfect phylogeny in 1991. And I think it's an obscure paper, wasn't even cited in your book. But at any rate, it goes in the following way. You simply recode each one of the sites of the data into now 3 binary sites. And these are just indicator vectors indicating which of the taxa have state 1, 2, or 3. I'll show you an example in a minute. And then the crucial theorem is that there is a 3-state perfect phylogeny for the original data if and only if there's a 2 or a binary state perfect phylogeny for some subset of this new data M prime, where that subset consists of exactly 2 of the columns of these 3 for each original column I of M. Okay, that's a mouthful. Here's that data again. Here's how it's been expanded into 3 columns. A has been expanded into 3, B is into 3, and so on. And you have indicator variables here to say who has state 3, who has state 2, and so on. And here is a compatible subset of 2 columns per triple, okay? And this is in fact the 2 that was illustrated in that tree. Okay, well, I can convert this. This is pretty easy to convert to an integer program because we have all that stuff for compatibility. So now we have 3 variables for original column I, 3 variables which are going to say, which 2 of these am I going to take? And that's the inequality which says I've got to take 2 of them. And this one is the inequality that says that if 2 of these new columns, one for I and original column I and one for J, where this is X and Y are either 1, 2, and 3, if any pair of those are in conflict, or incompatible, sorry, then I can't take both of them. So that's the inequality which says don't take 2 if they're incompatible. And of course, you have all the other machinery about missing values and so on, which sets this variable there. That's building on the binary case. Okay, so from the Dress and Steele theorem, this works. I'm going to have to speed up just a little bit. Handling missing values, again, you just have the variables that set the values, and now you say, for the 3 that were expanded from from a single entry in the original data that was a question mark, I want to make exactly one of those set to 1. The others are going to be set to 0. And okay, so everything makes sense. Minimizing the number of columns to remove. I don't have time to tell you, but all these things are minor twiddles on the previous stuff, and you just build and build. Okay, let me show you the empirical stuff without which I wouldn't be talking, because in the end, this stuff works. And so up to, here's just sort of illustrative, and I have to stop soon, but here are some experiments of 50 rows by 25 columns. This is in data where there is a 3-state perfect phylogeny, 100 by 50 where there is a 3-state perfect phylogeny, and this is the percentage of missing values. So this is way under a second, way under a second. As we increase the number of missing values, we're going up to 56 seconds. But for 20% missing, we're still, basically 1 second. Here it's 13 seconds for this size data, and then we're starting to hit where things are exploding. This is less than an hour. And then in data where there is no perfect phylogeny, the time values were similar, but in fact faster. Okay. This is results about removing columns. And again, everything is in the practical range. 3 seconds, 13 seconds, 49 seconds, for up to 15% missing values and so on. This is a 30 by 100 case, 100 by 50 case, under a second, and so on. R value here relates to how we generate data. The larger the R, the less tree-like the data. Okay, I can't tell you about the 4-state except that we build on the Kanan-Warno 1991 solution for 4 states, and the high-level idea, which has to do with enumerating tree types. And I can encode that into the integer program as well. And let me just go to the last slide here. The empirical data for that approach is a little bit smaller, but 30 by 30 solves in less than a second. And less than a second when there's no 4-state solution. So 0.2 seconds when there is. 50 by 50, these are averages over 100 data sets randomly generated. 50 by 25, again under a second, under a second. And then this is the question of removing columns. In a 50 by 25 case, this is actually when you shouldn't, because R is equal to 0, you should never have to remove any columns. Again, it's under a second. 50 by 25, when we're increasing the recombination rate of R, 23 seconds. 1 second, 3 seconds. And then up to 100 by 50, it's taking 70 seconds, but this is a large R as well. So again, I just want to say, in my view, this works. For this size data is big enough to have some practical applications and can be embedded in other things, in other software to generate these, at least for the binary, is up on my website. I'll put up the other ones later. And the binary case is, as I said, was published in Cocoon about 6 weeks ago.